Hello viewers, in today's class we are going to discuss yet another important and conceptual problem from definite integrals involving greatest integer function, right? So now here we have a problem that is integral from 0 to 1, and here we have two terms, right? The first one is the greatest integer of x square, and the second one is the greatest integer of x square plus half, and both these terms are added together. So we have to find the definite integral of this entire function, which is the sum of two greatest integer functions from 0 to 1, and the result is equal to lambda minus 1 over lambda, where lambda is some real number, right? So we have to find the value of lambda. Now here what we will do, we'll first take this integral as I, right? So I can be taken as integral from 0 to 1, and here we have greatest integer of x square, and then we have the greatest integer of x square plus half, and here we have dx, right? Now viewers, in our earlier videos we have studied how to calculate the definite integrals of greatest integer function, right? And here if we look at this integral, see, we can solve it the normal process of solving this integral may be like this, that is 0 to 1, and we have the greatest integer of x square. Here we have dx, and then we have 0 to 1 and greatest integer of x square plus half dx, right? So now if we go by this method, we have to calculate two integrals, right? This is the first one and this is the second one, and then we have to add the results of these two integrals, right? So this would be a very lengthy process. So in order to avoid this lengthy process, we'll make use of the important property of greatest integer function, right? So we are not going to adopt this method, that is first finding out this integral, then finding out this integral, and then adding up both the results, right? So instead what we will do, we'll make use of one important property of greatest integer function, and the property, it goes like this, right? So if we have any real number, say p, p belongs to the set of real numbers, then the greatest integer of p plus greatest integer of p plus half is equal to the greatest integer of 2 times of p, right? So this is the property which we are going to use to evaluate this integral, right? So if we have any p belonging to the set of real numbers, then the sum of the greatest integer of p and the greatest integer of p plus half, then the sum of these two quantities must be equal to the greatest integer of twice of p, right? So we'll make use of this property, and here if we take p is equal to x square, right? See, x is some real number, so obviously x square is also a real number, right? So we'll replace this p by x square. So if we take p is equal to x square in this property, then we have greatest integer of x square plus greatest integer of x square plus half is equal to 2 times, that is 2x square, right? So the greatest integer of 2x square. So therefore now our integral I can be written as integral from 0 to 1, and for this term we have only this expression, right? So here we have greatest integer of 2x square dx, right? So viewers, we have to now solve this integral only, right? So now what we will do in order to solve this integral, we'll make use of the method of substitution, right? So let us substitute y is equal to 2x square, right? So when y is equal to 2x square, then x square is equal to y over 2, and this is x is equal to square root of y over square root of 2, right? And now if we differentiate both sides, that is dx over dy, because we need to calculate dx, so dx over dy is 1 over square root of 2, and for the derivative of square root of y, we have 1 over 2 times square root of y. So we have now 1 over 2 root 2 and square root of y, right? So now dx can be replaced by dy over 2 root 2 times square root of y, right? Okay. So now see here x varies from 0 to 1. So let us change the limits accordingly. So when x is 0, so y is equal to 2 times of 0 square, because here we'll take x is equal to 0 and y is 0. When x is 1, then y is 2 times of 1 square, that is 2, right? So when x varies from 0 to 1, y varies from 0 to 2. So now our integral I is equal to 0 to 2, that is 0 to 2, and we have greatest integer of 2x square, and 2x square is y, so here we have y, and for dx we can write dy over 2 root 2 times square root of y, right? And now we can take this term 2 times square root of 2 outside the integral, so we have 1 over 2 root 2, and we have 0 to 2 greatest integer of y, and we can take this square root of y in the numerator, so we have y raised to minus half, and here we have dy, right? So now we have to calculate this integral. So now viewers, here we have I is equal to 1 over 2 root 2, 0 to 2, then greatest integer of y, and y raised to minus half dy, right? And here we see that the limits of integration varies from 0 to 2, right? So here y is 0, here y is 2, and between 0 and 2 we have the integer 1, right? So what we will do, we'll break this integral as a sum of two integrals. One is from 0 to 1 and other is from 1 to 2, right? So now we can write 1 over 2 root 2, and this integral can be written as a sum of two integrals, that is I1 and I2, right? And now I1 can be written as from 0 to 1, right? From 0 to 1, and we have greatest integer of y here, and y raised to minus half dy, and then I2 is from 1 to 2, right? So y is equal to 1, which is the integer between 0 and 2, is the point where we break the integral, right? So here we have 1 and here we have 2, and greatest integer of y, and y raised to minus half dy, right? Okay, so now we have two integrals, and in this integral we see that y varies from 0 to 1, right? So y varies from 0 to 1, and from the definition of greatest integer function, when y lies between 0 and 1, then the value of greatest integer of y is equal to 0, right? And when y varies from 1 to 2, that is 1 to 2, then again, by the definition of greatest integer function, the value of greatest integer of y when y varies from 1 to 2 is equal to 1, right? So we can also verify these values by taking some particular values of y between these two numbers, right? Okay, so now here greatest integer of y is 0, so this integral disappears. So now we have 1 over 2 root 2 I is equal to, and here we have 0 because greatest integer of y is 0, so this integral becomes 0, and here we have 1 for greatest integer of y, so we have 1 to 2 1 times y raised to minus half dy, right? So now this integral I becomes 1 over 2 root 2, and we have 1 to 2 y raised to minus half dy, and this is a very simple integral. So we have y raised to half over half, that is the integral of y raised to minus half is y raised to half over half, and limits are from 1 to 2, right? So here we have applied the rule, that is integral of x raised to n dx is x raised to n plus 1 over n plus 1, provided n is not equal to minus 1, right? So now taking this 2 to the numerator, we have I is equal to 1 over 2 root 2, and we can take this 2 in the numerator, and we have y raised to half and 1 to 2, right? And this 2 and this 2 get cancelled, 1 over root 2, and when we substitute the limits, and we'll take the difference, so here we have 2 raised to half minus 1 raised to half, and we have 1 over root 2, and this is square root of 2 minus 1, because square root of half is 1, right? So this can be written as square root of 2 minus 1 over square root of 2, right? And see, in the given problem, the value of this integral is given to be lambda minus 1 over lambda, right? So the value of this integral is square root of 2 minus 1 over square root of 2, and if we compare this expression with this one, that is lambda minus 1 over lambda, then we can easily make out that lambda is equal to square root of 2, and which is obviously a real number, right? So viewers, this is how we solve this important problem by making use of one important property of greatest integer function.